Is Muhammad Abdul Hamid. My ID is ET213022, and my partner is Nasser Ahmed Shaun, which ID is ET213032. And we have been supervised by Dr. Muhammad Shaimullah Chaudhary, and our research title is Enhancing Lead-Free Ba3BiCl3 Solar Cell via Hydrostatic Pressure, Material Insights, and Device Simulation. So, if we go to the further. Here is the presentation outline. The thing we are going to discuss here is introduction, objectives, methodology, device structure, and others as well. If you go to come to the introduction, here is the background. While metal halide Ba3BiCl3 offers high efficiency, their reliance on toxic lead and instability issues and development of robust eco-friendly alternatives. Research gap here is previous studies discarded as unstable, failing investigation how hydrostatic pressure could stabilize its and structure enhance its optical properties as well. Our current work is our research bridges this gap by demonstrating pressure-induced stability in the optimizing a device structure that achieves superior photovoltaic performance. And here is the research objectives. The first one is to study the material using computer testing, and the second one is to testing a solar cell with this material. The first one has been done by the DFT simulation, which is material study, and the second one is done by the Scaps we have simulated in the real life scenario. Here's the working flow. Here, the working flow starts from the Ba3BiCl3 material selection. At the very beginning, we have selected that material. After that, we have come to the first portion, path A, which is DFT, and we have applied the hydrostatic pressure from 0 to 5 GPa, which is gigapascal, and geometry optimization we have done in PBHSC06 two main method, and another method is LDA. Together with that, calculated properties, structure, electrical, optical, and mechanical as well. And using this data, we have gone to the path B, device simulation with Scaps. Define a structure. We have defined the structure with ITO, zinc, sulfate, Ba3BiCl3, spirometred AU. And with this format, we have varied the DFT parameter here and simulated PV performance with VOC, JSC, short circuit current, and fill factor, power efficiency as well. And after all, we have optimized the parameter with the variable of thickness, defects, and pressures. And after that, methodology of Scaps1D. The methodology of Scaps1D is we have very first launches the Scaps1D software. Initial working condition we have varied in ETL, HTL, absorber, ITO, indium tin oxide, and black metallic container as well. This is our material configuration. After that, define required parameters and defect to each layer, optimize thickness and defect density, convergence calculating with single shot and multiple shot as well. Simulation result from the simulation result we have got open circuit voltage, short circuit current, fill factor, and IV curve, JV curve actually. Device structure, here's the device structure. At the very top we are getting the sunshine, which is around 1000 watt per meter square, and we have transpired it into the ITO, which is around 500 nanometer. After that, ETL, zinc sulfate, which is around 75 nanometer thickness, and our Ba3BiCl3, the main material here is Ba3BiCl3, which we have optimized at 1100 nanometer. After that, HTL spirometer, which is around 200 nanometer, and we use AU gold as a black metal contact. So overall, this is the device structure. And if we go to the energy band diagram, where how actually electron has been gone from the absorber layer to the indium tin oxide, this is the process. There is the minimum band minimum band alignment, and after that same for the hole transfer, where hole is hole can easily go through this particular way. And after that, there is a material parameter. The material parameter we have used here is for 3 GPa, 0, 2, and 3 GPa. And for 3 GPa, we have calculated this from our particular simulation. We have used our MATLAB software here and other for the calculation as well. And remaining we get from the previous work. And if we come to the resultant analysis, here's the structure analysis. We can see at the left side lattice constants here from 6.2 to 6.8 variation, and lattice volume at the right side, which is around 250 to 310 Armstrong per cube. And you can see that the drastically pressure with respect to the pressure, lattice constant and lattice volume both has been gone down. Here lattice constant has been represented by green color, and lattice volume has been represented in red color. And in the right side you can see that the bond actually how actually bond has been responded with respect to the pressure. We can see that beryllium and bismuth, which is initially around 3.356 Armstrong, and after that to 5 GPa the bond length has been reduced to 3.181, and same for other as well. If we come to the band gaps pressures, here we can see that with respect to the pressure, direct band gap has been reduced from 1.70 electrovolt to 1.13 electrovolt. It has been done for same for HEC06 GGAPB LDACAP method. And if we closely look at the right side, here we can see that how actually at the initial position 0 GPa band gap is looking like. Here's the band diagram for minimum conduction layer and balance band conduction layer. We can see that it is around 1.696 electrovolt for 0 GPa, and for 5 GPa it has been reduced. It is reduced a lot. The bond gap between the conduction band and balance band has been reduced, and it is around 1.129 electrovolt. And if we come to the phonon stability conversion, here we can see that at the left side for it is unstable for 0 GPa. We can see negative frequency below the 0 frequency, which is defined as imaginary phonon, and for that imaginary phonon we cannot get a stable material. And if we apply some kind of pressure which around 2 GPa, more than 2 GPa, we can convert the unstable material to stable material. And furthermore, if we come to the if we can see that increasing pressure eliminates negative frequency, achieving full phonon stability from more than 2 GPa actually. And here is the charge density. We can see that at the initial position there is no covalent bond, all that are forming ionic bond before pressure. And if we give some pressure here, we can see that at the right corner here, right bottom corner, Ba and Bi has been converted to covalent bond from ionic bond. So it is the another finding here. After that optical parameter, we can see here the left figure 10 is indicating optical absorption at the very first wavelength. We can see that from 100 to 200 nanometer with respect to the pressure, we can see that absorption rate is high enough. And if you go to the reflectability layer, optical reflectability, same is for optical reflectability. And if we come to the optical parameter here, conductivity, we can see that if we zoom into that particular one from 100 to 200 nanometer, we can see that with respect to the pressure, the 5 pressure GPa is indicated in orange color. We can see the conductivity has been risen from 2.0 to 2.5 and more. So it optimized our conductivity actually. So if we come to the mechanical property here, the initially mechanical property is brittle, showing us the brittle conditions, and we after the pressure it converted into ductile transition. So what is the brittle and ductile? The brittle is mentioning that something that can be easily breakable, and ductile is something that is not easily breakable, that just with respect to pressure just it deforms. And it can be verified from the Fug ratio and Poisson's ratio. According to that ratio, the Poisson's ratio, which is around more than 0.26, is considered as ductile, but we can see that at 0 GPa the Poisson's ratio is 0.22, and after 3 GPa it has been up to it has been made the required conditions, and same for Pug ratio as well. And after that, if we come to the performance in solar cell, which we have optimized in the Scaps 1D software, we can see that with respect to the pressure, short circuit current is increasing, and same we can see that the open circuit voltage is reducing with respect to the pressure. Fill factor is initially it was rising up to 2 GPa, and after 2 GPa it has been reducing again. And if we come to the best optimal efficiency, you can see that in 3 GPa merging all the short circuit current open circuit voltage and fill factor, merging all that things together, you can see that efficiency comes across 28.89% at 3 GPa, which is a lot. So peak performance in summary, we can get that efficiency is 28.89% at 3 GPa, short circuit current is 33.53 milliampere per centimeter square, open circuit voltage is around 0.098 volt, and fill factor is 86.28%. Comparison, here's the comparison. We can see that the crystalline silicon crystalline silicon efficiency is around 27.9%. In it has been updated in 2025, and Ba3BiCl single junction solar cell is 26.95%. It is actual practical, and Ba3BiCl silicon tandem is 34.85%, and Ba3BiCl tandem is around 30.1%. And our research actually showing that 28.89% for Ba3BiCl single junction, which has been done in International Islamic University, Chittagong. And if we come to the key findings here, the key findings here is we apply hydrostatic pressure. Pressure external pressures is induced, modify, and the structure achieves phonos. We achieve the phonos here, and we also can see that band gap narrows from 1.70 to 1.13 electrovolt. And optical absorption also improved in our particular research. Peak performance is around 28.89%, and after that we can see that dynamically unstable, which is it was initially dynamically unstable, and after the pressure we convert it to the stable material, which is the key finding here. And the summary of the finding. So here's the summary of the finding here. We can see that for the first time we have converted the unstable material to stable material, and we also find a very optimal efficiency for 28.89% for this particular material, Ba3BiCl3. And the future direction is many of the material are not yet done with this research. So if we can convert some unstable material to stable material with respect to pressure, it will be much more effective, and we can do much more. We can get much more effective efficiency from the more great combination of Scaps 1D different layers. And here's the publication status. We are going to publish in the solar energy materials and solar cells, which is around Q1, and here's the reference as well. Then this is, thank you so much. I hope all of you have understood all the things which I have transformed here.